Let's do a practice problem. So we want to estimate the population average for a population. We have taken a sample. The average of the sample is 85. The size of the sample is 64. The standard deviation of population, suppose it is known and it's equal to 8. We want to build a 95% confidence interval to estimate the population mean. So I'm going to give you the formula here. So please pause, work on this problem, try to find the lower limit and upper limit of this confidence interval, and then come back to check the solution. All right, so let's see the solution. So the only thing that we need to do, we're gonna plug in all the information that we have. So we're gonna plug in X bar here, and then we have to compute Z of alpha over 2, the critical value, and we already actually found it from the table if you remember, that's 1.96. We also have sigma here, so we're going to plug it in here. And n is also 64, we're going to plug it here. And then we can compute the lower limit and upper limit. The lower limit is 83.04. The upper limit is 86.96. So a 95% confidence interval for this example is this range here, between 83.04 to 86.96. We say this is how we would interpret it. We say that, okay, we don't know what mu is, but we are 95% sure or confident that it is a value between 83.04 and 86.96. Next practice problem. So we want to again estimate a population's average, and we have taken a sample. The sample average is 125. The standard deviation of the population is 24. The size of the sample is 36. And we want to build a 99% confidence interval to estimate the population average mu. So we have the formula here. So please pause, go ahead and find the 99% confidence interval, and then come back to see the solution. All right, let's see the solution. So the only thing that you need to do here is just plug in these values that we have. X bar is 125, sigma is 24, and n is 36. The only thing that is missing is Z of alpha over 2. We have to find it. What is it? We need to find that and then plug it in here. So we're looking for a 99% confidence interval. That means alpha is 0.01%. That's 1%. So we're looking for Z of half of alpha, alpha over 2, which is equal to Z of 1% divided by 2. That's 0.005. So we need to look at the table and find the Z table and find the Z of 0.005. And that is equal to 2.58 if you look at the table. And if you plug it in this formula, we're going to get the lower limit and upper limit of the confidence interval. So the lower limit is 114.7 and the upper limit is 135.3. So this is our confidence interval. We would say we don't know what really mu is, but we know that we are 99% confident that it is a value between 114.7 and 135.3. Next practice problem. The manager of a paint supply store wants to estimate the actual amount of paint contained in 1-gallon cans purchased from a nationally known manufacturer. The manufacturer's specification states that the standard deviation of the amount of paint is equal to 2% of a gallon. A random sample have taken of 50 cans, and the sample mean amount of paint per 1-gallon can is 0.995 gallon. We want to construct a 99% confidence interval to estimate the population mean amount of paint included in 1-gallon can. So we know the formula for the confidence interval. You need to just plug in all the values, extract the values, and then find the confidence interval. So let's see what we have here. The average of this sample mean is 0.995. The standard deviation of population is 0.02 gallon, and the size of the sample is 50. So we want to build a 99% confidence interval for mu. So we have the formula, and we're gonna pick everything. Since we are looking for a 99%, that makes alpha 1%. Half of alpha would be 0.005, and z of 0.005 is 2.58. So we have the critical value. We're going to plug it in everything in the formula, and we're going to get the lower limit and upper limit. The lower limit of amount of paint per can is 0.988 gallon, and the upper limit is 1.002 gallon. The upper limit here doesn't really matter because a 1 gallon can cannot include more than 1 gallon. So we can actually modify this to just 1 gallon. So our confidence interval would be something between 0.988 and 1. We would say we are 99% confidence that the average paint is per can is something between 0.988 and 1 gallon. Next part of the question. Based on these results, do you think that the manager has a right to complain to the manufacturer, and why? So please pause and think about this question and then come back to see the solution. All right, so let's see the solution. So the claim made by the manufacturer is that the average population average of paint per gallon is 1 gallon per can. So the manager would have a right to complain if that's not the truth, but we don't really know the average of the population, the per gallon, a gallon per actually a can of paint. But we actually made an estimation, a confidence interval estimation, and the confidence interval estimation would include 1 gallon. So that means the manufacturer claims is kind of true. So the manager would not have a right to complain about the claim made by manufacturer. Next part of the question. Must you assume that the population amount of paint per can is normally distributed here? Explain. So please pause, answer this question, and then come back to see the solution. So let's see the solution. So here we don't actually need to assume the population is normally distributed because we can use the central limit theorem as the size of the sample is 50, it's greater than 30. So we don't need to make that assumption. Let's do a quiz now. True or false question. Sampling error can be eliminated if the sampling is done properly. What do you think? True or false? Well, this is false because the sampling method doesn't really matter here. The sampling error cannot be really eliminated. It can be deduced, but it cannot be eliminated. For example, you can decrease the sampling error by increasing the size of the sample. Next quiz. True or false question. The sampling error that comes from a random sample depends on both the variation in the population and the size of the sample being selected. True or false? What do you think? Think about this question. Well, actually, this is correct because the sampling error is sigma over a square root of n. So it both depends on the sigma, which is the size of the population, the variation in the population, and also it depends on a square root of n, which is the size of the sample. The square root of the size of the sample. So it's a true statement. Next quiz. True or false question. Taking a larger sample will always result in less maximal sampling error or error bound, but costs more money and take more time. Is this true or false? What do you think? Well, actually, this is false. The reason for that is it says always. Okay. On average, this would be true. So if instead of always it said on average, then it would be true. So that's the key mistake made here. So on average, if you take a larger sample, it would result in a smaller sampling error.